All right, let's take a look at some reactions of alcohols. And the first thing you need to know about alcohols is the way they react with acids and bases. And so it turns out that alcohols aren't strong acids or strong bases. So number one, alcohols are not strongly acidic and they're not strongly basic. They actually kind of behave like water. And you know that water is neutral. It's not an acid or it's not a strong acid. It's not a strong base. But it says here, their behavior in acid-base reactions greatly depends upon what other species are in solution. So again, an alcohol is not a strong acid or a strong base, but if you put it in the presence of a strong acid, an alcohol will act like a base. And if you put it in the presence of a strong base, the alcohol is going to act like an acid. And so we best describe alcohols as being amphoteric. And amphoteric means that they can be either acids or bases. Okay, they can either be acidic or basic, right? You think about amphibian, right? Can live in water or land. So amphoteric means some kind of molecule that can behave as an acid or a base. So check this out. So if we take an alcohol and we put it in the presence of a strong acid, and this is what's being represented here by the HX, this would be our strong acid. In that case, the alcohol becomes protonated. So we take our alcohol, this is our hydroxy group, and we add a proton. So instead of having OH, we have OH2, and that causes the oxygen to gain a +1 charge. And we end up losing the X piece as an anion. So that could be chloride from hydrochloric acid or bromide from hydrobromic acid. Now, if we think about an alcohol behaving as an acid, it says here for an alcohol to be deprotonated, the base must be stronger than hydroxide. And so if we have some kind of base that is stronger than hydroxide, and you remember that hydroxide is OH minus, okay? And there are several bases that are stronger than hydroxide. Well, in that case, the base can remove the proton from the alcohol. And in that case, we're going to end up with our oxygen now with a negative charge and we're going to have the hydrogen attached to our base. And you can see this here with phenol, and phenol is a weak acid. If we put phenol in water, we end up losing the hydrogen from the alcohol and the phenol. And so that tells us that water is actually behaving as a base in this case, okay? And so it ends up producing hydronium. So H3O plus, we call that a hydronium ion. Hydronium, okay, hydronium ion. And we end up with a negative charge on what was formerly our alcohol, but now we have a negative charge on our oxygen. And so it says here that phenols typically act as weak acids. So again, we see this reaction between the phenol and water, where the phenol loses the proton to water, so that means water is the base. And then we also see this reaction between phenol and potassium hydroxide. And keep in mind that hydroxide is an extremely strong base. And so it's going to pull the proton off, or the hydrogen atom, I should say, off of the phenol. And so there's some words that you hear probably that are trying to come out of my mouth, that maybe are things above the level of this class. But another way you can think about an acid, okay, an acid is going to be a H plus donor, okay? It's going to be an H plus donor. And a base is going to be an H plus acceptor. H plus acceptor, okay? And if you look very carefully, you'll see that, right? You see that in the first reaction, we have our base, and the alcohol is actually behaving as an acid. Why? Because it's donating this H plus ion, right? It's donating the hydrogen so that we end up with O with a negative charge, right? Anyhow, same thing here. You can see the phenol is behaving as an acid. Why? Because it's donating this proton, right? Anyhow, just another way to think about an acid and a base. So again, an acid is a proton donor and a base is a proton acceptor. That whole idea, that concept of proton donor, proton acceptor was developed by Bronsted and Lowry. All right, ethanol. Ethanol is often used as a solvent in medicines and has antimicrobial properties due to its abilities to denature proteins in organisms to predict the major product of the following reactions of ethanol. So ethanol says here used as a solvent in medicines. Ethanol is also the alcohol found in alcoholic beverages. So this is ethanol here. So both of these reactions involve ethanol. And the first one, we're going to react it with hydrochloric acid. And the second one, we're going to react it with this carbon that has a negative charge on it here. And so you remember that what we said before, when you react an alcohol with a strong acid, is the oxygen is going to gain a hydrogen atom like this. And so we're going to have a positive charge on our oxygen. And then we're going to be left over with our Cl minus ion like that. Okay. Now, if you have a negative charge on carbon like this base is much, much stronger than the hydroxide ion. And so, again, as we saw before, when we had a base, there was something that was a stronger base than or sorry, stronger base than hydroxide, the alcohol is going to be behaving as our acid, our proton donor, and this anion here is going to be behaving as our base, right, our proton acceptor. And so when we're done, we're going to have our negative charge on our oxygen, right, because it's going to have lost H plus, okay? Then we're going to have lithium, the lithium cation, to balance out that negative charge. And then we're also going to form propane, right? Because once this gains one proton or one hydrogen atom, we call that propane. All right, let's talk about dehydration reactions at 180 degrees Celsius. Now, I'm sure that everybody's hearing this video has done enough strenuous exercise in their life to know that dehydration means what? Loss of water, okay? But now, instead of, going out and doing strenuous exercise and a human being losing water, we're going to talk about molecules losing water. Namely, we're going to talk about alcohols, okay, losing water. So a dehydration reaction is one in which water is chemically removed from a compound. The reaction can occur in two different ways depending on the reaction temperature. At 180 degrees Celsius, we're going to generate an alkene as the predominant product. So let's take a look at the general reaction here. We have some kind of alcohol, and then we cook that up with H2SO4, which is sulfuric acid. So sulfuric acid, okay, at 180 degrees Celsius, and we end up pulling off the hydroxy group and a hydrogen off of the next door neighbor carbon, the neighboring carbon atom, to form H2O, and then we're going to form a double bond between the two carbons. Now, if you take a look at this specific example that's shown here, we have 2-butanol, right? Where does that name come from? I have 1, 2, 3, 4 carbons, so my hydroxy group is on carbon 2, so 2-butanol. Well, if we're going to do a dehydration reaction with sulfuric acid at 180 degrees Celsius, we're going to lose water, right? We're going to lose the hydroxy group that's attached to the yellow carbon, which would be what I described in a previous video as the carbonyl carbon. But you see, you have two next door neighbors. You have the one in green and you have the one in purple. And so both of those next door neighbors have a proton to give up to form water. Well, if we were to remove the proton, sorry, the hydrogen atom, and I keep calling them protons, which is an appropriate term. If I was to remove this one here, then my double bond is going to be between the green and the yellow carbon. And so this would be my product. If conversely, let's say I was to remove this hydrogen on the neighboring carbon that's in purple, I'm going to form my double bond here, right? And I'm going to end up with this compound. Okay, kind of tough to squeeze it in that box, but anyhow, so you can see that in this case we end up with an alkene, but it's a different alkene, and you can see their names here, 2-butene and 1-butene respectively. And so you can see here that one of them is the major product, right, which is formed in a much greater yield than the minor product that's only formed in about a 10% yield. Well, why is that? The reason why is the double bond between the green carbon and the yellow carbon. Those two carbons are attached to more carbons overall. Look, if we take a look at the green carbon, okay, meaning this one here, and the yellow carbon here, how many total carbons are they attached to overall? Well, the green carbon is attached to one outside of the double bond, and the yellow one is attached to one outside of the double bond. Okay, so it's attached to two groups overall, two alkyl groups, two groups that are carbon based. Whereas if I look at the green, or sorry, the yellow carbon here, it's attached to one carbon based group. But if I look at the violet or purple carbon here, it isn't attached to any carbons outside of the double bond. And so here, between these two carbons, the yellow and the purple, they're only attached to one group. Okay, and there's names for these products. The one that has the more groups, We call that the Zaitsev product, and the one with only one group, that's called the Hoffman product. But all you need to know is whichever double bond has the most carbon atoms attached to it overall is going to be the major product. All right, menthol is a component of ointments like Vicks VapoRub, which are used to ease minor muscle aches. Predict the major product of the following reaction of menthol. So we're taking menthol and we're heating it up with sulfuric acid. So if I highlight this carbon in blue, okay, this carbon is attached to the oxygen of our alcohol. Now we know when we lose our water, we're going to take the OH from this alcohol, but we also need another hydrogen, right? Because you need H and OH, right, to make water. So where is the other H coming from? Well, remember, I told you it can only come from the next door neighbors. You have one neighboring carbon here, and you have another, I'll use my black pen, you have another neighboring carbon here. Well, the carbon in red has a hydrogen atom drawn on it, which isn't shown. And the carbon in black has two hydrogen atoms that are neither of them are shown. And I'll just put one in for instructional purposes. So if we were to do the dehydration, the loss of water, pulling off the red proton, right, then our double bond would be here between the red and the blue carbon. And so let's draw what the product would look like. So we would have our double bond here. Okay, we've lost our OH, we've lost our H. And so now I'm going to have my CH. Oops, I made a mistake there. CH. It's an isopropyl group, isn't it? There we go. So we have our isopropyl group, and we're going to have our methyl group down here. Now, if we were to pull off the proton in black, in that case, our double bond is going to be here. So let's draw what that would look like. So our double bond would be here. We have our CH3 group or our methyl group here. We have our isopropyl group up top, like that. There we go. So now which one of these is going to be the major product? Well, I'll help you out. The product in red is going to be the major product. Why? Because if you look at the two carbons in the double bond, I'll highlight this one in yellow and this, or sorry, this one in green and this one in yellow. Well, the carbon in green is attached to two carbons, right? It's attached to this carbon and this carbon, again, going away from the double bond. And the carbon in yellow is attached to this carbon here. And so we would say it is tri-substituted. Let's put here tri-subs, like that. If I look at the product in black, okay, if I highlight this carbon in red and this carbon in blue, for example, the carbon in red is only attached to one carbon um, outside of the double bond. And this carbon is also only attached to one carbon. So we would say that this is the minor product because why? It's not tri-substituted, it's di-substituted. So di-substituted. Now, the next one is if we turn down the heat and we try a dehydration reaction at 140 degrees Celsius, in that case, we're going to take two alcohols and join them together to form an ether, and we'll end up losing water in the process as well. So you see that shown here. If we have an alcohol and an alcohol, we react them together, you can see the OH group from one of the alcohols and the H from the other alcohol. That's going to leave to form water, and then you're going to form a bond between this oxygen and the R group. Maybe we could do a better job of that. And this R group like this to give you an ether, all right? So this is another type of dehydration reaction. Why is it dehydration? Because we end up losing water as a product. You can see an example here. This is ethanol. So we have two molecules of ethanol coming together. You can see that they've highlighted the blue hydrogens and oxygen that are going to be removed to form the water, right? And to form the diethyl ether, all you have to do is form a bond between this carbon and this oxygen here, and that is going to give you the diethyl ether. Now, it says here that historically, diethyl ether was used as an anesthetic during surgery. Diethyl ether is no longer used as an inhalation anesthetic because of its flammability, so it really limits your ability to smoke a cigarette while you're performing major surgery. All right, predict the major products of the reaction shown. So if we take a look at this alcohol, this would be isopropyl alcohol, isopropyl alcohol, and notice that the temperature is 140 degrees Celsius. And so what's going to happen is we're going to bring two molecules of isopropanol together. I'll just draw them like this, okay, just to kind of help illustrate the point. Okay, so here is oops, our two molecules of isopropanol. So we're going to end up, when we react those two together, okay, we're going to end up losing H2O. So I'll put this here. So we're going to get H2O, but we're also going to get a bond between this carbon and this oxygen like this. So that would give us what we call diisopropyl ether. So I'll just scribble it down here. So I have CH3, CH, and then we're going to have all the same components over here. So this would be called diisopropyl ether. All right, let's move on to oxidation of alcohols. And we're going to start with oxidation of a primary alcohol. So make sure you know what a primary alcohol is. I went over that earlier. So it says here, an oxidation reaction occurs when a molecule gains oxygen atoms or loses hydrogen atoms. So that will be our definition. Oxidation is going to be when a molecule gains oxygen or loses hydrogen. Primary alcohols usually generate carboxylic acids through an intermediate aldehyde. So here we have our primary alcohol. You can see the carbonyl carbon, the one attached to the oxygen, is only attached to one carbon, right? So that means it's primary. And this O in the brackets here, or parentheses, that represents oxidation. So it's just generic oxidation, okay? And you can see the primary alcohol gets converted into an aldehyde, and then it gets oxidized again to a carboxylic acid. So an example would be ethanol, which is the alcohol found in alcoholic beverages. Inside your body, it's actually oxidized to acetaldehyde. Acetaldehyde is largely responsible for a hangover. Anyhow, and then the acetaldehyde is further oxidized to a carboxylic acid. So you can see that this is oxidation because as we go from the ethanol to the acetaldehyde, we lost hydrogens, didn't we? Look, we have one, two, so look, count. One, two, three, four, five, six hydrogens in ethanol, but if we look at acetaldehyde, we have one, two, three, four. So we lost two hydrogens. Therefore, it's proof that it's oxidation. Now, the number of hydrogens didn't change when we went from acetaldehyde to acetic acid, but we did gain an oxygen, didn't we? Right? We gained this oxygen here, further proof that the second reaction is also an oxidation. Secondary alcohols generate ketones as their final products. So we see a secondary alcohol here. Our carbonyl carbon is attached to two carbon-based groups. We have our oxidation. And so again, we're losing two hydrogens, right? We're not gaining any oxygens, but we're losing these two hydrogens here. Therefore, this is oxidation. And a specific example would be 2-propanol, which is rubbing alcohol. It undergoes oxidation to give you acetone. And again, you can see that you've lost these two hydrogens here, right? In 2-propanol, we have a total of 8 hydrogens. So I'll put here 8 hydrogens. But in acetone, we only have 6 hydrogens. 6, come on, 6 hydrogens. So again, you can see that we lost hydrogens, therefore this must be oxidation. And the last point is students love rules where there's no exceptions, and a tertiary alcohol is a rule where there's no exceptions. Tertiary alcohols do not oxidize, okay? So you can't oxidize a tertiary alcohol. Again, primary alcohol will give you an aldehyde followed by a carboxylic acid once it's completely oxidized, and a secondary alcohol will give you a ketone. Okay, example 9.7, draw the structural formulas for the final product of the following reactions. So this first one, you can see that we have a primary alcohol, right? This is a primary alcohol. How do I know that? I know the carbon that is attached to the oxygen is only attached to one carbon. And so my primary alcohol is going to give me a carboxylic acid. Now, I'm not going to lose any carbons along the way. So I know I'm still going to have my one, two, three, 4 carbons like this. And on this carbon that's attached to the oxygen, this one here, that is the one that's going to be oxidized to a carboxylic acid. So I'll convert that into into a carboxylic acid like this. Then I just need to add my hydrogens to the other carbon. So this one will have one, this one will have three, and this one will have three. All right, the next example, we have a secondary alcohol. You can see that your carbonyl carbon, the one attached to the oxygen, is attached to one, two carbons. And so therefore, secondary alcohol is going to be oxidized to give us a what? A ketone, right? So we're going to start by drawing out, we have our one, two, three, four carbons like this. We have this one down here. And if I use my green highlighter for the carbon that's attached to the oxygen, this one here, that's going to be converted into a ketone like that. And so now I just need to add my hydrogens in to the other carbons, and there you have it. And so here's a little summary of what we've covered in this video. If we take an alcohol and we treat it with sulfuric acid, so H2SO4 is sulfuric acid, we're going to do a dehydration reaction. If we choose a temperature of 140 degrees Celsius, we're going to lose water, dehydration, but we're going to form an ether. And if we do it at a higher temperature, 180 degrees Celsius, we're going to form an alkene. Okay. If we do an oxidation, so some kind of oxidation, which remember is gain of oxygen or loss of hydrogen. If we have a primary alcohol, it gives you an aldehyde, then it further gets oxidized to a carboxylic acid. If you have a secondary alcohol, it gives you a ketone. And if you have a tertiary alcohol, it does not oxidize at all.